Dear students, we have started with aromatic hydrocarbon. This is the last chapter, last portion of this chapter, and with this we will come to the end of class 11 syllabus. Aromatic compounds. Which are aromatic compounds? We have already discussed while discussing in the class. Huckel rule of aromaticity helps you to understand whether a compound is aromatic or not. So the compounds which we shall be studying are benzene, that is C6H6. As you know, each corner here occupied by a carbon and hydrogen. The carbon is sp2 hybridized. So the third bond, which is not shown here, that is occupied by hydrogen, is a bond line structure. The next one is benzene ring with a CH3, where one of the hydrogens of the benzene ring has been replaced by CH3, and so molecular formula is C6H5CH3, that is called toluene. Then is naphthalene, which we very commonly used pesticide at home, especially in the toilets, in the cupboards, to prevent from insects bite. So this naphthalene is a fused benzene ring with the molecular formula C10H8. Here you can notice that the molecular formula, the carbon is more than hydrogen. Okay, in hardly any compound you find where hydrogen is less than carbon. The next compound is biphenyl. When two benzene rings are attached by a single bond, then it is called diphenyl or biphenyl. You should be very clear about this naphthalene and biphenyl. Okay, they are not same. This biphenyl will be requiring quite often in the class 12 chapter. The next we take some of the substituted benzenes. If you see, if another hydrogen of toluene is replaced by another CH3 in the neighboring carbon, we call it 1,2-dimethyl benzene, and common name is xylene. Okay. Now orthoxylene means the two CH3 groups are in the nearest neighbors. Now this way we can remove the position of CH3 from 2 to 3, then 3 to 4, and that's how we get 1,3-dimethyl benzene and 1,4-dimethyl benzene, as they are all position isomers. And this is metaxylene and paraxylene, commonly known as. Now let us talk a little bit about the structure of this benzene ring. As you know, here the benzene ring has a 6-membered ring structure, and since each carbon is sp2 hybridized, the unhybridized p orbital is shown above and below the plane. As you can see here, these are the unhybridized p orbitals, which is perpendicular to the benzene ring. You can imagine a sleeping benzene ring, and p orbitals, unhybridized p orbitals, are above and below the plane, and each of the orbitals are occupied by a electron. Okay, now since all these p orbitals are parallel to each other, they might overlap and form one pi bond. These two might overlap, form another pi bond. These two may overlap, form another pi bond. So that's how you get 3 alternate pi bonds. But it is not necessary that only these will be overlapping. The overlapping may be in a different manner also. How the overlapping may take place? The overlapping may take place like this. This overlapping, and this overlapping. So you can see the position of the double bonds will keep on changing, and that is why we consider it to be a cloud. Okay, it is a pi cloud above and below the ring. So it is a kind of sandwich structure. The 6-membered ring is in the middle, and the pi cloud is above and below the plane. So next we go to preparation of benzene. The first two methods are already done before. The first method is cyclic polymerization of ethine, which you have done in the previous class. So when ethine is passed over red hot iron means iron at very high temperature, and it forms benzene. Second method is decarboxylation of aromatic acids, which we have done for the preparation of methane, where we took not aromatic acids, we took aliphatic acid. And here we get when sodium benzoate, that is the sodium salt of benzoic acid, is heated with soda lime. Soda lime, you remember, NaOH and CaO in the ratio 3:1. It forms benzene. The third reaction is new to you. Benzene ring with OH is called phenol. It's an aromatic alcohol. Then phenol, when heated with zinc, zinc is a reducing agent here, it forms benzene. That means it is capable of taking away the oxygen, and the hydrogen gets attached to the benzene ring. And with this 3, we come to the end of the preparation of benzene. Not too many. Physical property, I request you to do it on your own. Then we move to chemical properties. I'll not be discussing all the chemical properties of benzene, but we shall be discussing the reactions which will be requiring in class 12. Benzene, though you can see it has so many multiple bonds, 3 multiple bonds. So we know that they can be considered as unsaturated hydrocarbons, and the speciality of unsaturated hydrocarbons is they undergo addition reaction. But that is an exception here. Benzenes do not undergo addition reaction, rather they undergo substitution reaction. Because if they undergo addition reaction, when the pi bonds break, they lose their aromaticity, and aromaticity leads to stability. So they don't want to remove the aromaticity so that they become unstable. Now what kind of electrophilic substitution reaction they undergo? They undergo substitution by electrophiles, and we call it electrophilic substitution reaction. So here, as you can see, benzene ring, each of the corners are occupied by 1 hydrogen. So any of the hydrogens from here can be replaced by any other electrophilic group, which we represent by E+, and we get various kinds of substituted products. Very, very important. Okay. So we shall be discussing 5 reactions: halogenation, nitration, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. So here we have the halogenation reaction. So as the name suggests, you need a halogen. That means you are replacing the hydrogen of the benzene ring by a halogen. So the commonly used halogens are either chlorine or bromine. And it also demands a Lewis acid catalyst. And here we have chosen the Lewis acid catalyst to be anhydrous AlCl3. Now remember, since we have taken here chlorine, that's why we have taken AlCl3. If I take here bromine, then we will go for AlBr3. Like that, we will change the halogen depending on the requirement. Now, as I said, the electrophile is Cl here. So, hydrogen will be replaced by Cl, and you get chlorobenzene. Okay. And the byproduct will be HCl, which I have not written. In organic reactions, quite often we do not write the byproducts. The next reaction is nitration. Nitration means your electrophile is NO2 plus. Now here, how we bring this NO2 plus? For generating this NO2 plus, we need concentrated sulfuric acid and nitric acid mixture, which is commonly known as nitration mixture. So can you see here the benzene ring and the hydrogen is replaced by NO2. Now I have written NO2 here, but you are free to put NO2 anywhere else because all the corners are equivalent here. Alright. If you wish, you may write here, doesn't matter, but only one NO2 at one time. Then the third reaction is sulfonation reaction. So in sulfonation reaction, how we generate the electrophile? We take the reagent which we take here is called fumic sulfuric acid, also called oleum, and its molecular formula is H2SO4.SO3. If you add them up, it becomes H2S2O7. So in different books, you may find different notations written, but it means the same thing. And the product which you get here is benzene with a SO3H group called benzene sulfonic acid. SO3H group is called sulfonic acid group. Next, benzene undergoes Friedel-Crafts reaction. It's a name reaction. As I said, there are 2 types, alkylation and acylation. Alkylation, as the name suggests, you are introducing an alkyl group in the benzene ring. That means your electrophile is an alkyl group. I have taken here the alkyl group to be CH3. So the reagent needed is haloalkane, that is CH3Cl, together with the same Lewis acid catalyst, anhydrous AlCl3. So the product which you get is, as your alkyl group is CH3 here, so you get a CH3 group here. Okay, and the name of the compound is toluene. If you want C2H5 in the side chain of the benzene ring, then you should begin with C2H5Cl or Br. Similarly, acylation reaction, when we do, CH3CO group is acyl group or acetyl group to be very precise. In general, we write RCO group. So it gives you a ketone, and the ketone out here is acetophenone. Benzene ring with COCH3 is called acetophenone. As you can notice here, there is a ketonic group. So the name is ended with -one. It's a acetophenone. Very, very important compound, and very often we make mistake. So these are the 5 reactions. Now what we need to do is learn the mechanism of these reactions. So there are 3 steps in all the reactions. Step 1 is generation of electrophile, E+. Step 2 is electrophilic attack. That means how benzene ring gets attached to the electrophile. And step 3, deprotonation. As you know, the hydrogens are replaced by the electrophiles, so the hydrogen has to go. And removal of hydrogen is called deprotonation. Now benzene ring, in general I have written benzene plus E+, that is the electrophile, giving you the electrophilic substituted product. Let's begin with the first reaction, halogenation reaction. Here I have taken with chlorine, the example with chlorine, but the mechanism I have given it bromine. Similar reaction, you can always replace the halogens by chlorine can be replaced by bromine, bromine can be replaced by Cl, no problem. So here benzene ring plus bromine, as I mentioned earlier, here please ignore this Br2, twice you need not write, since you have written once you need not write again. In your copy you can do the correction. So here we have taken AlBr3 because the halogen out here is bromine, and the product which we get is bromobenzene. Now how we generate this bromine as a electrophile, because halogens are usually negative, but here we are getting positively charged halogen. So here we come to, you see, bromine, we know it's a halogen, so it has 7 valence electrons, out of which 1 is involved in bond formation, remaining 6 remain as 3 lone pairs in each of the bromines. Now this AlCl3, we know that it is having sp2 hybridization. So one of the p orbitals, as you know, p orbitals are 3 in number. So the third p orbital which has not taken part in hybridization remains perpendicular to the plane of AlBr3. Now aluminium, its octet is not complete. As you can see, there are only 3 bromines around it. So it has a tendency to complete its octet. As a result, this Br tries to give its electron to this empty p orbital. And what happens? This Br-Br bond becomes weak. As you can see here, the bond between bromine and bromine becomes weaker, and we have written here bond breaking, and bond between bromine and aluminium becomes stronger, bond forming, because bromine has valency 1, it cannot form 2 bonds. So finally the bond between bromine and bromine breaks, and we get AlBr4 minus. Minus because 1 pair of electron we are getting from bromine. And this Br is left with a positive charge, and that's how we are successfully capable of generating the electrophile. Step 2, electrophilic attack. You see, in the benzene ring there are 3 pi bonds. You are free to break any of the pi bonds heterolytically. So I have shown this pi bond is breaking, going to this corner, and this corner carbon becomes negative and it attacks the Br plus, and the positive charge on Br gets neutralized. And what we get here? We get a positive charge at this corner because this corner has lost the electron, and we have shown the hydrogen also together with the bromine. This bromine got attached to this corner. Whichever corner will attack the electrophile, that corner will get the electrophile. Now this particular positively charged carbocation will stabilize itself by a process called resonance, which we have done in last year. Please check, resonance we have done, to form a resonance stabilized sigma complex. This is the sigma complex. There are 2 ways sigma complex can be written. Another way is this. So what is the difference between the two? In one you can see we have shown delta plus in 3 different corners wherever they have acquired the positive charge, and here we have shown delta plus at the center. Both means the same thing. But when drawing the dotted lines, you need to be careful. The dotted lines should be from where the positive charge has began till where the positive charge has ended. Okay, so when you draw the dotted lines, you must be careful. Okay, one ortho position to the other ortho position. Now that's how we get the second step done. Now third step, deprotonation. That means removal of the proton. Actually this AlBr4 which is formed here, it has to give you back the AlBr3 because it is a catalyst. That is the speciality of a catalyst. That means it has to be regenerated at the end of the reaction. So this AlBr4, what does it do? It takes up the H plus, which I have not shown, okay, and gives the electron of H plus to the ring, and it regains its aromaticity, and you can see here I have not shown the double bonds anymore. I have drawn the circle, which shows that the electron pair has come back to the ring and it has stabilized itself. And the H plus I have written, you may write HBr also, no problem. Next is nitration. How we generate the NO2 plus. In the nitration reaction, H2SO4 and HNO3 both are needed, which is known as nitration mixture. H2SO4 dissociates to give you H plus and HSO4 minus. The structure of nitric acid we have written as, instead of writing HNO3, we have written HONO2. Now the lone pair on this oxygen, it can attack this H plus, and you can see here we have the oxygen with 3 bonds. So oxygen acquires a positive charge. And you know, oxygen is basically an electronegative element, and it is with a positive charge now, has strong tendency to pull electron towards itself. As a result, this water will separate out. I think it is very clear that this is actually looking like water, H2O. So when water goes off, you are left with NO2 plus. So you have successfully generated the electrophile. Now step 2 will be similar. The pi bond will break and attract the NO2 plus and it will give rise to the sigma complex. Step 3, same thing. It will give you the deprotonation product and you will get NO2. In sulfonation reaction, it is, as I said, it is slightly different because your electrophile is a neutral electrophile here. So H2SO4.SO3 simply dissociate to give you H2SO4 and SO3, which is the neutral electrophile. The structure of SO3 is written here. You can see S with the 3 double bonds with oxygen. The hybridization of this S is sp2, and you can see its octet is not satisfied. Why its octet is not satisfied? Because the pi bonds are not considered to decide the stability by octet. Okay, so we can see there are 3 bonds. That means it has its sextet complete, not the octet. So the pi bond breaks as usual in the other structures, as we have discussed in the other structure. Pi bond of the benzene ring breaks, attacks the sulfur. Now the moment the benzene ring attacks the sulfur oxygen bond has to break. Otherwise sulfur will have 7 bonds around it, which is not possible. So now the moment sulfur oxygen bond breaks, we get a negative charge on oxygen, and what we get is SO3 minus. And then again the resonance stability we have to show to form the sigma complex. Now step 3 is slightly different again. Since the SO3 itself carrying a negative charge here, it attacks the H plus, forms SO3H, and the electron pair comes to the benzene ring to regain the aromaticity. So that's all about sulfonation reaction. Now Friedel-Crafts alkylation and acylation is very similar to halogenation. You see, in halogenation also we needed AlCl3 or AlBr3 as we have taken here. Here also we have the halogen. Here we have the halogen and here we have the AlCl3 also. So here we had only halogen and here we have haloalkane, CH3Cl. So the sp2 hybridized AlCl3 has an empty p orbital. It takes in the electron from chlorine. Then CH3Cl bond becomes partially weak, and AlCl3 bond tends to form, and ultimately AlCl3 pulls the electron towards itself and forming CH3 plus, so electrophile is generated. Now I have written here, try step 2 and step 3 on your own, exactly the same way as we have done before. Acylation reaction is also very similar. The starting material is CH3COCl. These Cls also have 3 lone pairs. It is again having AlCl3, and this AlCl3 is taking in the chlorine, lone pair of the chlorine, and again the partial bond breaking, bond forming taking place, and we have generated the electrophile successfully here. Now for this one also please complete step 2 and step 3. Now one very important thing which is there in the textbook and we have discussed while discussing resonance in the chemical bonding chapter in class 11. Please do study. Okay, very important, directive influence of functional group in the monosubstituted benzene. That means if you already have something in the benzene ring and if they need to undergo halogenation, sulfonation, nitration reaction, then where the electrophile will get introduced. It cannot get introduced wherever you feel like. Alright. And then I have given some exercise question. It will be a pleasure if you send after working it out. And with this we come to the end of class 11 syllabus. Now we are ready to start class 12 syllabus, and I'll be sending you the PDF for this. By Wednesday you must be ready with that. I'll be sending the video after that.